So, we saw that the term defect structure hides in it a lot of details, and if we really want to understand properties of materials, we perhaps have to understand this defect structure. So, what is my pathway to understanding this defect structure? As we said, the first thing we will do, of course, take up isolated defects. These isolated defects could be vacancies, dislocations, they could be stacking faults and other kind of defects, which we will take up one by one very soon. We will try to understand their charge associated with them, the stress fields associated with them, the energy of those defects, etc. The next stage after taking up an isolated defect would be to take up perhaps a pairwise interaction. That means I may take up, for instance, a vacancy and its interaction with another vacancy. Of course, even in a pairwise interaction, often, as we shall see very soon, that there are certain global considerations, especially for instance, if we are talking about would a divacancy form. Then for instance, we also have to consider the entropic term, and as we all know, entropy is a statistical system wise kind of a calculation. That means I have to look at the global picture as well, even in an what you might otherwise think to be a interaction between two vacancies. Of course, then we can consider interaction between, for instance, like for instance a vacancy and a vacancy cluster. They could have a vacancy cluster having a lot of vacancies, and I can talk about its interaction with an isolated vacancy. So, for instance, this vacancy cluster could grow, actually it can emit vacancies and it can shrink. So, there are these various possibilities, but I need to now then talk about an individual vacancy with a vacancy cluster. An important other, for an example of an, for instance, pairwise interaction between two kind of defects would be, for instance, a dislocation interstitial solute interaction. And we will see later, for instance, this can lead to an important phenomena known as the yield point phenomena when you are talking about a stress strain diagram for mild steel, and what you might otherwise call an uniaxial tension experiment for mild steel. So, we start first of all with an isolated defect, a vacancy, a stacking fault or a dislocation, try to understand its stress fields, its energetics, its charges associated with them, etc. Then we talk about pairwise interaction, and this pairwise interaction would perhaps lead me to a larger assemblage of defects, and we had seen that while talking about that we not only have to talk about interaction, but association of these defects, and this association can lead to a larger cluster of defects. For instance, a defect structure which is slightly more complicated, or it has many other defects associated with each other. Then when I am talking about this pairwise interaction, again I obviously worry about the stress fields, energy and charge, etc. And then once I am done with this task, I can now proceed to a larger global picture wherein I am talking about behavior of an entire defect structure with external constraints. That means I have to worry about, for instance, when I am applying stress on a material, then I have to understand how this stress can affect motion of a single dislocation. I need to worry about the collective motion of large number of dislocations. I need to worry how these dislocations interact with each other, and what other kind of other defects or other kind of structural changes in the dislocation line can be brought about by these interactions. So, but as we shall note, this is actually a very difficult problem in material science. This is not a very easy problem, and there are good attempts going on at the various length scales now, but this is definitely not a solved problem of material science. And I said one of the important problems now being considered is the collective motion of dislocations. And the thing we would worry about when talking about collective motion of dislocations is obviously plastic deformation and also work hardening. So, when I am talking about this collective motion and external constraints, external constraints could be forces, they could be electromagnetic fields, any other thing which could affect my dislocation structure in the material, and I am worrying about long range interactions in that case, and I am also worrying about collective behavior. So, there are two important things which I need to worry about when I am talking about this large scale problem of defect structure, especially the behavior of the defect structure under external constraints. So, this is my global thought process I would undertake when I am going to understand this problem of defect structures, but as I said, we shall start with a simpler understanding wherein we consider isolated defects, and more often than not, some of these considerations are more than enough for understanding certain kind of phenomena. So, the next thing we take up is that how can we classify defects in materials. Okay. There are very many ways of attacking this problem, many perspectives towards understanding defects in materials, and each one of them perhaps throws light or brings to focus certain aspect of the defect. Of course, we will start with something known as the dimensionality of the defect, and as we shall see, this is a sort of an ideal geometrical definition. We can talk about them with their association with symmetry and symmetry breaking, how certain defects lead to symmetry breaking and how they are associated with certain kinds of symmetry. We can talk about them based on their origin. Of course, this word origin here is defined as slightly different sense the usual sense, and we will see in what sense are we talking about the base on the origin. We can talk about based on their position. Of course, when we defined a crystal, we said whenever we are talking about a crystal, we always talk about a crystal if the motif is actually a geometrical entity, a physical property, or a combination of both. And similarly with the defect, we have to worry about is the defect with respect to a physical property, or is it something related only to a geometrical entity. So these are questions I would ask myself, and I would classify my defects based on these very many criteria. Of course, we have noted that this is a sort of an elementary introductory course on the subject of structure of materials, and therefore we will not consider all the possibilities in detail, but it is very important that the broad overview is in focus or kept in mind when you are studying the details later on. So even though some of the concepts we are introducing in this next few slides are what you might call a broad umbrella kind of description of the subject, that means there are a lot of definitions which we will not consider in detail, but please do keep in mind some of these definitions even though we may not consider them in detail in this course. So let us start by sort of classifying defects based on dimensionality. So we could have 0-dimensional defects, 1-dimensional defects, 2-dimensional defects, and 3-dimensional defects. Again, as we know, dimension is a really speaking a geometrical kind of a definition. In other words, when I am saying 0D, I do not really mean 0-dimensional. What I mean is point like. And when I am saying 1-dimensional, what I mean essentially, for instance, suppose I am talking about displacement fields associated with the defect, then I would think that the displacement fields are line like. Okay. And similarly, when I am talking about a 2-dimensional defect, I do not really mean it is an exact geometrical 2-dimensional surface, but what I mean is that it is almost 2-dimensional. So that is what we mean by this, these lower order dimensionality of defects, and this kind of a classification is very important, because that throws in view most of the kind of defects we will normally deal with in material science. 0-dimensional defects could be, for instance, a vacancy. It could be one of those alloying element atoms we have seen before, like a substitutional element or a interstitial element. Then in charge systems we will see there are additional defects like Frenkel and Schottky defects. So these are so there are possibilities which are only possible in charged materials, which is Frenkel and Schottky defects. 1-dimensional line defects, which are very important as far as material behavior goes. There are 3 important ones: the dislocation, the disclination, and the dispiration. In this set of slides and in this course especially, we will focus basically on the dislocations, but we need to remember that there are other possibilities like disclinations and dispirations. Surface defects, when I mean surface, sometimes I may use the term loosely surface. What I mean is an interface defect, and surface being a special case of an interface between a material and vacuum or material and air typically, and that I call a surface. But we have to remember, when I am saying a surface, it is actually many times just I am talking about an interface. So, and we had already noted that, for instance, a surface is an inevitable defect in a material. So there is always going to be a surface in any real practical material. Then there is a possibility of an interface between one material and another material, which we call an interface material. For instance, on one side of the boundary, a flat 2-dimensional boundary, I could have copper, other side I could have aluminium, and that would be an interface boundary. Then there could be a boundary between 2 materials of the same kind. That means there could be one crystal on one side with respect to another crystal on the other side, which is misoriented with respect to the other 2 crystals are misoriented by some angle, and therefore that I call a grain boundary. Then if the 2 materials have a special kind of a symmetry relation on each side of the boundary, then I call it a twin boundary, and typical twins would say, for instance, be mirror related twins. Then there are additional defects which are stacking faults, which come up in the order of stacking, and there are special other kind of boundaries, special cases of stacking fault which are known as anti-phase boundaries. When you are talking about 3-dimensional or volume defects, we have already seen that one kind is which is unavoidable is thermal motion or thermal vibration. So one kind of 3-dimensional defect is always present in a material, and whenever I am talking even about a lattice or a crystal, I am actually defining a crystal with respect to an average position of atoms, and therefore thermal vibration is definitely going to distort your that ideal crystal with respect to those lattice positions. The the entire volume of a twin within another material can be a defect, which I call a twin. The boundary itself we saw is a two-dimensional version, which is called a twin boundary, but the entire twin which is present within another material is called which itself could be a defect. Then a precipitate, for instance, a second phase within a larger matrix could be a defect in the crystalline order of the matrix. The faulted region, for instance when I talked about a stacking fault, the faulted region could be a 3D volume defect. Voids and cracks are 3D volume defects, and therefore there are many possible defects based on dimensionality. So may I ask a question?
What is meant by dispersion and disclination?
Yeah, what we will do, this is just a broad overview picture. Here I am trying to show that actually defects can be classified based on dimensionality, and we have considered some names for now. We are not defined, we are not even defined what is a vacancy, though we have seen what is an impurity. We also know what is the surface, for instance, from common experience, but we have not defined most of these things. So we will take them one by one up, but with regard to your special question of what is a disclination or dispersion, we will define them very soon when we talk about line defects. But more importantly, we will not go into detail of dispersions and disclinations, while we will take up dislocations in detail. So we will take up those definitions very soon. Okay. So, but this is a broad understanding overview of the possible defects and a way of classifying them based on dimensionality. Of course, if you want to specific answer for now, disclination is a defect associated with the rotational symmetry of the crystal, associated is the word, and dispersion is a symmetry associated with the screwed symmetry of a crystal. Okay. Now, so perhaps the next slide answers your question much better here. So we can classify some of these defects based on their association with certain symmetries of the crystal. So the dislocation is a defect associated with translational symmetry, disclination is a defect associated with rotational symmetry, and dispersion is a defect associated with screw symmetry. And in talking about these symmetries, I am talking about the atomic level or the symmetries at the crystallographic level, but essentially at the atomic level. But I could also have symmetry associated defects which are rather multi-atom or slightly larger picture or larger length scale, and we could have twins which are mirror symmetry related twins, we could have rotation symmetry related twins, and we could have inversion twins. Though often the most common kind which material science we deal with is a mirror twin, but we should not forget if there are two regions in a crystal, because usually in typically in contact, and if they are related by a symmetry operation, then that's two variants can be called twins. So the symmetry operation relating the two crystals could be inversion or a rotation or a mirror. So we will consider some of these in detail later on. This is something again we will not talk about detail, but just as maybe a slide in the passing, so that we at least know that there are certain kind of defects based on what is known as symmetry breaking. So there are defects known as topological defects, and there are non-topological defects, and a defect associated with the symmetry operation of the crystal is called a topological defect. So this is just a definition, and perhaps mostly in this course we will not further use many of these terms, but just to note that when I am talking about a when you come across literature where they are talking about a topological defect, they typically mean it is a defect associated with symmetry of the crystal. This slide is actually an important slide, and we will take up some examples of some of these when we go to the individual defects. For instance, defects can be based on origin, we can define them, or based on position we can define them. So we had said this before. When you are talking about based on origin, and of course I do not mean origin means how they came about to be in the material, but by their very definition you will understand what I mean by the word origin here. So defects can be what you might call statistically stored defects, or they could be structural defects. Now there is an important distinction here, because and of course there is a very closely related term to structural defects, and sometimes the term used is geometrically necessary defects, and especially with regard to dislocations a term is used called geometrically necessary dislocations, but I would like to distinguish geometrically necessary defects from structural defects, and I will call these structural defects clearly to distinguish or use a distinguishing name. For instance, I am talking about vacancies. Now vacancies could be statistically stored, as you know their origin in the crystal could be because of thermodynamics, the entropic stabilization they can provide, and we will soon when we talk about vacancies we will see how they are how we can calculate the equilibrium concentration of vacancies in a material. So at any finite temperature you will have a certain concentration of vacancies, and these vacancies arise purely because of thermodynamic requirement, or in other words the configurational richness, and in other words entropy increase they provide. So, at every finite temperature you will have a certain concentration of vacancies. These vacancies are typically randomly present in the crystal. So, they are statistically stored, they could be present anywhere in any of the lattice points, and for instance at a given temperature they may also move around. Now, a structural vacancy on the other hand is not present because of thermodynamics of the system, it is because, for instance, we will take up examples, they may be present because of off-stoichiometry. That means, if I have a compound like, for instance, typical example with nickel NiAl, and I do not have a perfect 50-50 composition, I have an off-stoichiometric composition. This off-stoichiometry is accommodated by the presence of vacancies, and those vacancies are typically localized to a certain sublattice, and therefore, they have a different origin, and their role in diffusion is, for instance, very different from the statistically stored vacancies. Therefore, when I am looking at properties, when I am looking at I have to distinguish, or I have to make this distinguish between a structural and a statistically stored dislocation or defect, and good example would be dislocations. For instance, when I grow a crystal, typically it will never be perfect. For instance, I solidify a melt of aluminium, I would find that it has lot of dislocations. Typically, we will see the density of these dislocations could be about 10 power 3 meter per meter cube, or 10 power 4 meter per meter cube, or in that range of values. Now, apart from these kind of statistically, because these dislocations could be present anywhere in the crystal, these I could call a statistically stored dislocation. But we will see dislocation could have a totally different origin. For instance, if I have a misorientation between two grains of a crystal, what I might call a misorientation typically less than about 10 degrees, this misorientation can be accommodated by an array of dislocations, but these array of dislocations are localized to the interface between these two crystals, and therefore, this dislocation is performing a structural role in the material. It is accommodating the misorientation. It could also accommodate misfits, it could, as we shall see soon, and other kind of rotations. Now, these dislocations are not the statistically stored dislocation, and they can be clearly seen that, suppose I am talking about the role of these dislocations in plasticity, then this dislocation wall, which is now the low angle grain boundary, would be very different in behavior as compared to the statistically stored dislocation in terms of their effect on plastic deformation. So, or in simple externally applied shear stress, the shear stress at which statistically stored dislocation may move, it could be very different from a dislocation which is present in a dislocation wall. So, we could have statistically stored dislocations and structural dislocations, or statistically stored defects and structural defects, and we need to differentiate them because of their role they play in material behavior. Now, again based on position, in some sense these two are very closely related, like but we will try to differentiate the two, that based on position again defects could be random or ordered. Now, for instance, suppose I had vacancies. Now, vacancies, as I said, could normally be present in a random fashion, but suppose and it could happen that in a certain system, and typical examples of vanadium carbide systems, wherein these vacancies could get actually ordered. That means, the vacancy would have a sublattice for itself, and therefore, in the process of this ordering, obviously you know the symmetry of the structure would change, and which could lead to a change in the crystal structure. And any, for instance, beautiful examples we will consider later of defect ordering would be stacking fault ordering, which could again alter the crystal structure, but we have to remember that this is now based on the position, and once a defect gets ordered, it cannot be treated like an ordinary random defect, because it is now going to change your entire crystal structure, and if the crystal structure is changing, obviously the properties are going to change. So, for instance, to give a nice example, as I said, the vacancy ordering phenomena, wherein, and they have vacancy ordered phases apart from vanadium carbide also from aluminum, copper, nickel kind of systems, and you would notice that once the vacancies have got ordered and they have a sublattice, I can now even talk about a hierarchy of defects. In other words, first of all, of course, I have a vacancy which has got ordered. Now, I have a sublattice for the vacancies. Now, there can be a vacancy in the vacancy sublattice which would actually be an atom. So, I can now talk about a hierarchy of these kind of defects, but I need to remember, now once the vacancies have got ordered, they have a profound influence not only in the crystal structure and therefore on the behavior of the material. This next slide relates to the way these defects are defined, and we have seen that we could we have been talking that actually that we can actually define a crystal, and hence for instance a motif which contributes to the formation of crystal could be actually a physical property. So, we seen the crystal could be defined based on a geometrical entity or a physical property. And when I am talking about if the crystal is defined with respect to a physical property, then the defect in that crystal will also be with respect to that physical property and not with respect to a geometrical entity. Of course, if the crystal is defined with respect to both the geometrical and the physical property, then geometrical entity and the physical property, then the defect also would be a combined kind of a defect. But let me take up an example wherein I am talking about a defect with respect to a physical property. A good example of this would be the domain wall in a ferromagnetic material. In a ferromagnetic material, there are regions wherein all the magnetization vectors are aligned. So, for instance, if you see the figure below, on the left hand side, which I call domain 1, you can see the domain 1, you can see that all the magnetization vectors are in the right hand direction, they point to the right. There could be a different domain, which is the one which is marked in green, which I call domain 2, wherein the magnetization vector is pointing in the opposite direction. Now, the region in between, which has been shown in gray region here, so you can see this gray region here, is the transition region, which is shown in projection here. So, this is my transition region. In the transition region, my magnetic moment vectors go from this pointing direction to the opposite pointing direction. Now, clearly this crystal, the way it has been defined, the ferromagnetic ordering is with respect to the spin vectors or the magnetization vectors, and therefore it is a physical property. Now, what happens in between this transition? Typically the vector rotates, and it rotates off the plane, and when the rotation is off the plane, it is called a block wall, and when the rotation is in plane, actually it is called a Neal wall. So, you see that there is a block wall which is forming here, which is a domain wall, and clearly this is a defect with respect to the perfect ordering, either with respect to domain 1 or domain 2. The ordering in the domain wall is not perfect, it is actually changing its orientation from position to position. So, this defect, the domain wall, is clearly a defect not with respect to the geometrical entity, it is with respect to the physical property, which is now the magnetization vector or the spin vector, and therefore I can also talk about defects with respect to either the geometrical entity or the physical property. So, this also has to be kept in mind, though we shall not consider very many examples of these kind of defects in this course, but it has to be kept in mind. If my definition of the crystal itself involves a physical property, then there could be defects with respect to that physical property, and a very good example here is this domain wall. Okay. This is something, a word of caution perhaps, that whenever I am talking about a symmetry which is going on to define a defect, then the operation defining a defect cannot be a symmetry operation of the crystal. So, this point has to be kept in mind. For instance, a twin plane in a mirror twin cannot be a mirror plane of the crystal. So, this is perhaps somewhat obvious, but just to state it at the beginning, so that property of the which is closely related to the symmetry of the crystal. So, to repeat this note, that the operation defining a defect cannot be a symmetry operation of the crystal. In other words, for instance, a twin plane in a mirror twin cannot be a mirror plane of the crystal. So, this point has to be kept in mind. So, with this we come to the end of the broad introduction of what you might call defects in crystal. So, we have taken up a broad overview, but since we are dealing with so many concepts in this very classification, let me briefly revise the various concepts and try to see that how this forms the basis for some other important discussions we take up later. So, the thing we started off in this chapter, or the discussion of point defects, was that we can go from an ideal crystal to a real crystal, to which means that I have to introduce defects in the crystal. Then I go to the concept of microconstituents and microstructure. So, the important intermediate step is the formation of the real crystal, which is a defected crystal, and the need for us to consider this defects in crystal is its importance with respect to many properties, and especially those properties which we call the structure sensitive properties. And in this context, I had pointed out, when I mean a structure, I typically mean a microstructure. And when I am talking about defects, we also pointed out that and to just emphasize the point, for instance of the importance of defects in a material, we had seen that, for instance, suppose I am talking about yield stress in a material. In the absence of dislocations, the yield stress could be of the order of gigapascals, but when you have dislocations in the material, the yield stress could reduce and it could be of the order of megapascals. So, therefore, there could be a large change in the properties. Of course, the question we may, a more philosophical kind of question we can ask is that are these defects good or bad? It depends on the context. For instance, suppose I am talking about forming a component by plastic deformation, then I want the crystal to be weak, so that I can use a press which is of lower tonnage. Suppose I am talking about forging a crystal, I would use a lower capacity machine. That means I need to have a lesser investment on the capital cost, and the operating cost also will be lower. Therefore, in this context actually dislocations are good, because it gives me an easy plastic deformation. So, if defects are good or bad in a material, that actually depends on the context, and it is not a good idea to actually comment on that without actually considering the context. But we can clearly see that some of these defects play a very important role in the properties. Then we also talked about an important thing called this defect structure. That means that I can not just consider defects in isolation or consider defect and forget about its overall role in terms of its interaction with other defects, etc. So, the quantities, for instance, I needed to consider was the density and spatial distribution of defects. I needed to consider its interaction with other defects and its association with defects of the other kinds and its own kind. I need to consider, for instance, its dimensionality. I need to worry about is it a random defect or a structural ordered defect, or it's a statistically stored defect, or it's a structural defect. And when I have answers to all these questions, and I also consider what you might known as the collective behavior of dislocations, especially collective behavior of defects, especially under the influence of external constraints or external influences like magnetic fields and stresses, then I have a handle on the properties of the material. Therefore, I not only have to consider defects in isolation, but I also need to consider defect structure of the material. Then we went on to classify defects based on dimensionality, based on their association with symmetry, and we said that, for instance, a dislocation can be thought of as an defect associated with the translational symmetry of the crystal. Similarly, we also saw that twins can be inversion twins, mirror twins, or even rotation twins. Then we also saw that defects are sometimes classified as either topological or non-topological defects. We also considered the important aspect that when I am talking about defects, if I ignore their origin, or for instance, if I am talking or their order in the material, then I am making a serious mistake. In other words, a structural vacancy can play a very different role in the properties of material as compared to a statistically stored vacancy. And similarly, as ordered defect has a very profound influence right on the crystal structure of the material. Then we also said that whenever like in the definition of a crystal structure, we also need to worry if the defect is defined based on the geometrical entity or the physical property. And with that we come to a sort of a broad understanding of the overview of classification of defects in materials, and then now we will slowly take up one by one all the defects, and we will start with point defects. So, let us first take up point defects in crystal, which we might say are the 0-dimensional defects in crystals. So, we will start with the overview, then we will talk a little about vacancies and their clusters, interstitials, and other kind of defects in charged materials like the Frenkel defect and the Schottky defect. Though this particular treatment we are dealing with here is a very elementary treatment, for those who are interested in doing advanced reading in the subject, they can go refer to a slightly advanced text like the one by Lopez and co-workers, which is the point defects in materials. So, we have already seen that point defects are mathematically 0-dimensional defects. The more appropriate term is a term which we can call that these defects are point-like. In other words, the influence sphere of these defects spreads into only a very small region around a point, typically not more than a few lattice spacings around a single atom, for instance, and therefore, we can still classify them as point defects. And when later on also, when we are defining defects based on dimensionality, we have to notice that suppose I am calling a dislocation a one-dimensional dislocations, often the sphere of influence of a dislocation, especially for instance the stress field, could be very long distance. In other words, the stress field of a distance is a long range interaction and definitely not constrained to a line. So, the line in that case, what we mean is perhaps what if I am talking about edge dislocation is the line where perhaps the half plane of atoms end or a missing half plane ends. So, this is what we might call a working mathematical definition rather than a very real definition, but often you can see that this definition gives us a good handle on the classification, if not always on the understanding of the properties of the defect. Okay. So, when we say a line defect or a point defect, we mean it is point like or line like, okay. Or in other words, the essence of the defect can be understood in that dimensionality. We shall see that point defects could be associated with a stress field and a charge, and this is very, very important. For instance, like in the case of charge, we will see that there is something known as F centers which can impart color to a crystal, and the stress field is a very another important thing which a point defect could be associated with, for instance a vacancy, and it can interact with other defects in the material through this stress field, and this stress field obviously could be long range. It need not be confined to a few lattice parameters or so, and this long range interaction can actually lead to the evolution of the defect structure. So, when I am talking about point defects, I have to worry about the stress field associated with the point defect, and at times also with the charge associated with the point defect. The other important point which I mentioned when I was talking about point defects and other defects is that these could associate to form larger groups and complexes, and this is something very important, because the group behavior of these groups could be very different from the associated point defect. Suppose I have a single vacancy vis-a-vis a cluster of vacancies. Obviously, a cluster of vacancies is no longer zero dimensional. It is going to have a perhaps some sort of a two dimensional nature if it is confined to a plane, or it could even get into a three dimensional if it is more like a spherical association of vacancies. And therefore, the properties of the defect are considerably altered when they start to aggregate or they start to associate with each other. And this point is absolutely to be kept in mind, that am I talking about an isolated defect, for instance a point defect, or am I talking about an association of these point defects or any other kind of defect. The other important thing is that often when these defects associate, they can be even the language for their description can even change. For instance, vacancy clusters in a crystal plane, we shall take up this actually in detail later when we talk about dislocations, can actually now be visualized not as just merely a vacancy cluster, but also as a edge dislocation loop. And we shall see in FCC crystal, for instance, this edge dislocation loop is something known as the Frank partial dislocation loop. So, when I am talking about dislocations, I need to worry about the stress field, I need to worry about the charge associated with them, I also need to know how they are associated with other point defects and other kind of defects in the material. And more importantly, sometimes the language used to describe these clusters changes, and the nice example for that could be the vacancy cluster on a crystal close packed crystal plane in FCC crystal, which can be visualized as a Frank partial dislocation loop, which would be a what you might call a disk of vacancies. So, we already seen this slide, but now we will take up examples and consider a little more detail about for instance structural and statistical vacancies or structural and statistical defects. And we had already, of course, we have seen this aspect. So, just to this is perhaps a revision, but we have a nice example here in the case of a structural vacancy. Now, for instance, as I said, suppose I am talking about a point defect, and one of the point defects, let me maybe consider that point defect first. So, the most important point defect would be, perhaps to start with, could be a vacancy. A vacancy is, for instance, an atom missing from a site. So, you can see the figure below that the region here where an atom is missing is a vacancy. And whenever I remove an atom from the lattice position, then obviously the atoms around it would not remain in their equilibrium position, they would also move, and this would create a certain kind of a displacement field around the vacancy. Now, so with this basic definition of vacancy, let me go back to the classification of point defects based on origin. Now, we already seen that the statistical origin is because of thermodynamic reasons. For instance, you could talk about, of course, in case of vacancy there are thermodynamic vacancies which are created purely because of Gibbs energy minimization. But of course, you could add an alloying element for an interstitial alloying element which could again go and sit in a random position. Now, a structural vacancy, for instance, is, as I pointed out, can arise because of stoichiometry. That means, suppose I take an NaAl compound which is a B2 structure, that means it has got an ordered CSCl structure, which we know is two interpenetrating simple cubic lattices, one with the origin at 0, 0, 0 and one with an origin at half of half. So, in other words, it is an ordered BCC ordering of a disordered BCC structure which becomes simple cubic. Then in NIL kind of structure, you can have, it is not a purely a stoichiometric compound, that means it is not a line compound and it can accommodate considerable of stoichiometry. That means it can get Ni rich or it can get aluminium rich. The aluminium rich compositions, it is noticed, are result from vacant nickel sites. Suppose I want to make aluminium rich composition, there are two possibilities for me. Either I can start putting aluminium in nickel sites, which would give me a richness of aluminium, or I can start removing atoms from the nickel site, which will also make it stoichiometrically aluminium rich. But in the case of nickel aluminium, there is of course an asymmetry with respect to aluminium rich compositions and nickel rich compositions, the way they are accommodated. The aluminium rich compositions are accommodated by vacant nickel sites. So, this is found energetically favorable and therefore, you have vacant nickel sites, because now these vacant nickel sites are not coming because of thermodynamic reasons, not because they give rise to an increase in entropy, but they are coming because of the off stoichiometry and therefore, they will be localized to the nickel sublattice. Of course, they could be disorderly present anywhere in the nickel sublattice. So, they are in that sense random within the nickel sublattice, but their origin is purely because of the off stoichiometry. Now, that means that suppose I am talking about diffusion, and therefore, this vacancy cannot jump to the aluminium site, which jump to the aluminium site would be energetically unfavorable. Now, similarly, when I am talking about vacancies as I pointed out can get ordered, and typical examples of these vacancy ordered phases are aluminum copper nickel alloys, and there are specific compounds like V6C5 and V8C7. So, whatever I told in general was true for classification of defects in general is also true for point defects. Now, point defects could have intrinsic or extrinsic source. In other words, this is additional thing we need to consider when I am talking about classification of point defects. Now, if I am talking about intrinsic defect like a vacancy, then no additional atom is involved. So, they could, these intrinsic defect could be vacancies, they could be self interstitial. In other words, what is self interstitial? An atom which is supposed to sit in the lattice position has been displaced and it sits in the interstitial position. So, this does not involve an addition of an additional atom, and this would call as self interstitial. So, this is an example of an intrinsic point defect. Anti-site defect is also an intrinsic point defect, and this is found only in ordered alloys or compounds. For instance, suppose I am talking about this NiAl, which I saw in the previous slide. So, I have a specific sublattice, a simple cubic sublattice for nickel, and there is a specific aluminium sublattice for aluminium. Suppose nickel goes and sits in the aluminium sublattice, this would be called an anti-site defect, and obviously like all the vacancies and self interstitial, they cost energy to the system and they are unfavorable. That means, if I take the system to a global energy minima, then self interstitials and anti-site defects would be annihilated. Vacancies, as we shall calculate to an equilibrium concentration, would persist because they are thermodynamically favorable defects. Extrinsic defects, on the other hand, involve atoms from other species, and that means that, for instance, you could have an impurity atom or an atom which you can call a dopant or an annoying element or an impurity, which can now of course go and sit in a pre-existing vacancy. It can go, if the impurity atom which I have added can go and sit in a vacancy, it can go and sit in the, for instance, interstitial position, or it could replace one of the existing atoms. So, all three possibilities exist. So, let me write down those possibilities. So, all these possibilities exist when I add an extrinsic kind of an element, that means which does not belong to the system existing. In the larger perspective, presence of a different isotope of a material, for instance, let me go back, presence of different isotope of material may also be considered as a defect. So, this thing has to also be considered, and this can be actually beneficially used in many circumstances as a tracer in diffusion, for instance. So, let us come to a different way of looking at point 0D or point defects. In ionic crystals, for instance, you have Frankel defects, Schottky defects and other kind of defects which are possible. In non-ionic crystals, we could have vacancy or an impurity, and this impurity we have already seen can be an interstitial or a substitutional kind of impurity. Okay. So, we shall basically start with impurities in non-ionic crystals, then proceed to defects in ionic crystals. Point defects can be created by removal, addition or displacement of an atomic species, and this aspect we already seen in the previous slide. For instance, we already seen that removal constitutes a vacancy, displacement constitutes a self-interstitial, and addition consists of an extrinsic kind of a point defect. So, we already seen this aspect, and we will also take up later on certain more complex kind of a defect point defect structures. So, we basically briefly considered this slide before, wherein we defined what is a vacancy, and we had noticed that the atoms around a vacant lattice site are displaced with respect to their equilibrium position, and this displacement field could exist. Predominantly the displacement field would be a small region around the vacancy, but could the effect could exist a little longer distance through via the long range stress fields. So, some of these things we already seen. So, I nearly need to revise that the vacancies can be, as I said, random or statistical or structural, or and we have seen these aspects. So, I need not go over them. The important role of vacancies is in diffusion of substitutional atoms, and this is very important. For instance, suppose I need to dope, for instance, silicon with some dopant to make it a p type or n type semiconductor, then often this diffusion of this species into silicon will take place through vacancy migration. That means, if a jump from vacancy from one side to another can be considered as an opposite jump for the atom. So, let me show this on the board to you. So, this is my perfect crystal, and say for instance, one of these sites is vacant. So, this is my vacancy. Now, my jump of a vacancy from here to here can be considered as a jump of an atom from here to here. So, this is something. So, after this jump has taken place, I can now redraw the picture, because now I consider these two atoms here. So, this is my initial configuration with the vacancy and an atom, and after the jump has taken place, the atom would be on the left hand position and the vacancy would be here. So, by this kind of successive jumps of the vacancy, I can consider diffusion to be taking place. Vacancies also play important role in various forms of creep, and this is something which has to be noted. Not only can there be equilibrium concentration of vacancies, that means vacancies can be present in the right concentration which can minimize the Gibbs free energy, but they can also be present in a higher concentration than dictated by thermodynamic equilibrium for a given temperature, and this can be obtained, for instance, by quenching from higher temperature. That means, I take my material to higher temperature where my equilibrium demands a higher concentration of vacancies, then I quench it to a lower temperature, and but then of course, all the vacancies may not be quenched in, many of the vacancies may quenched in, but this concentration of vacancies can be much higher than the one which is present at high temperature. Now, this obviously would mean that the diffusivity of the material which is higher concentration of vacancies would be much higher than, and now I am talking about the diffusion of substitutional atoms, would be much higher than the one which has just an equilibrium concentration of vacancies. But bombardment of high energy particles can actually lead to an enhanced concentration of vacancies, and this is very important, especially when we are talking about materials which are involved with nuclear reactors, etc. So, we can have an equilibrium concentration of vacancies or an higher than equilibrium concentration of vacancies, and I have just outlined two methods by which we can produce an higher than concentration of vacancies. Now, some of these aspects we have considered before. The important thing known as interstitial alloying element, we have also seen in what kind of sites, for instance, they would sit in a FCC crystal or a cubic closed pack crystal or a BCC crystal or HCP crystal. We have actually calculated the number of voids per atom, etc. previously. For instance, now if I try, and we have seen that when I try to put an interstitial atom, so let me show the interstitial atom sitting at the top here in this picture. So, I have an interstitial atom here. We can see that it is typically larger than the lattice position, and therefore, they cause stress fields and displacement around the position in which they sit. And This, as we shall see later on, is a very important effect, especially when I am talking about, for instance, carbon in steel and talking about the interaction of these carbon atoms with a dislocation core. So, this would be an important thing we will consider later, and this is coming from the long range stress fields of the dislocation, which is interacting with the stress field of the interstitial atom. This stress field of a interstitial atom typically has higher shear component as compared to a stress field which is around a substitutional atom, which is somewhat rather hydrostatic, and a substitutional atom could be larger than the atom parent host atom, or it could be smaller, leading to compressive or tensile stress fields. And it does make a difference to us if it is compressive or tensile. Of course, in isolation both of them would cost energy to an equal extent, but when I am talking about the larger picture of interaction between defects, it will now make a difference that where would this, for instance, substitutional atom segregate with respect to a dislocation line. Would it go into the compressive region of a dislocation, or would it go into a tensile region of a dislocation, would be determined by the relative size with respect to the parent atom. Now, examples of substitutional atoms we know, for instance, are copper sitting in the lattice site of an FCC nickel. So, this would be an example of substitutional impurity element. Interstitial element we have considered in detail before, like for instance carbon sitting in the octahedral void of high temperature FCC ion. So, we already dealt with these, and so we do not have to, just as a revision as before. So, when I am talking about an impurity atom, I need to know where does it sit. Additionally, what is its relative size with respect to the position where it is sitting, and hence the kind of stress fields it associated with. So, this is something which we need to consider. There are very specific cases wherein an atom, and this specific example would be for instance boron and steel, that atom can occupy both the lattice position and the interstitial position, and so there is a competition between its distribution between the interstitial and lattice positions, and these are of course rare examples wherein for instance this boron is one such example. This slide perhaps is just a revision of the previous slides, but now since we are talking about this slide in the context of point defects, it is worthwhile to revise this slide and to note the important point that when I am talking about, for instance, carbon sitting in an octahedral void in high temperature FCC ion, there are these compressive strains because the carbon atom is much larger than the void, and this would, we have seen, that limit the solubility to about 2-8%. So, this is something which we need to note. In BCC ion, the same strains are responsible for even lower solubility in ion. So, carbon is very less soluble in alpha ion, which is the BCC form of ion. So, understanding the relative sizes and understanding the kind of stresses and strains they produce, in other words understanding the energy cost of the system to accommodate this point defect, can tell me sort of the solubility of the system. When I am talking about this solubility, I am perhaps sometime considering much more solubility than what is simply entropically benefit, because we have seen that vacancies and similarly interstitials etc. can be entropically stabilized, and that solubility is very much fixed by the thermodynamic equilibrium. We ask the important question, because we have been mentioning this term repeatedly, which is the concentration of vacancies dictated by thermodynamic equilibrium. So, we ask this important question, and we did take up this topic somewhat when we dealt with the topic in the context of thermodynamics during an early introduction to this course. And the question we are asking again is that why are vacancies preferred in a crystal? The thing we need to understand obviously is that when I am putting in a vacancy, in other words removing an atom from the crystal, there are going to be broken bonds. There are going to be distortions of the bonds around the central atom. Suppose I am removing an atom from this position, for instance the central position, which is now the position of the vacancy here. Not only are the bonds broken around this, but there is a distortion of the bonds of these atoms, because now these atoms around this are going to be moving with respect to the atom which has been removed. Therefore, the whole system, it is going to cost me energy, and this energy or the enthalpy I call the enthalpy of formation of the vacancy, which I have give a symbol delta HF. And this enthalpy formation typically for various pure metals, for instance, is of the order of, for instance, between about 0.08 as low as 0.08 to about 1.74, which is for nickel, electron volt per vacancy. That means of course it can vary over an order of magnitude or more, and therefore delta HF can take various values, but nevertheless what it tells me is that there is a certain cost of putting vacancies in my crystal in terms of its energy, and this energy I am talking of course in terms of enthalpy. So, and you can see that the enthalpy cost is for these are of course FCC elements here, these two are HCP here, and some of these are different crystal structures. So, we can see that it varies a lot, and of course this depends on the strength of the bond. That means if, and because now I am distorting and breaking the bonds. So, if it costs me energy and hence enthalpy to accommodate vacancies in the crystal, then why are vacancies present in the crystal? Now, that means that there must be the other factor, which is now my entropy factor, and this entropy factor tells me that above 0 Kelvin there is an equilibrium concentration of vacancies, and the kind of vacancies we are talking about here are called the thermal vacancies. And why does this arise? As we said, is because of the entropic richness or configurational richness that the system is provided. If I take a pure crystal, and that means a crystal where all lattice points are occupied, a perfect crystal, and calculate the number of configurations possible, and that is just 1, which means that if I use Boltzmann equation S equal to k ln omega, then ln 1 will be 0. That means the system does not have any configurational richness, and therefore its entropy is low. Now, suppose I put in a vacancy into the system. This vacancy could sit in any one of the positions in the lattice positions, and all these would be energetically equivalent. Of course, in this case I am ignoring the surface of the crystal, and I am assuming that all positions are configurationally equivalent. That means by introducing a vacancy, the system becomes configurationally rich, and in this process the entropy of the system increases by introducing this vacancy. And since we know that for a system, when I am talking about if a system is stable or it is unstable, I am talking with respect to the Gibbs free energy. So, the parameter which characterizes the stability of a system is at constant temperature and pressure is the Gibbs free energy, which is applicable to condensed matter systems, and we would notice that in such a system it is better for me to accommodate vacancies in spite of the fact that it is energetically going to cost me. So, let us calculate the number of vacancies which are stabilized at any temperature T. So, let n be the number of vacancies and n be the total number of sites in the lattice, and we will typically start with configurations wherein the vacancy concentration is much less than 1, and we will also ignore, and for such an assumption we will assume that the vacancies are far apart, and therefore the interaction between vacancies can be ignored. That means delta HF is not a function of the concentration of vacancies. If I put the first vacancy, it costs me a certain delta HF. If I put the second vacancy, it costs me the same delta HF, because now these vacancies are far away and they do not interact with each other. So, the third vacancy, the fourth vacancy, all of them, the cost for me would remain identical, and that would be delta HF. Now, delta H for formation of n vacancies would be n times delta H for formation of one vacancy, and that is the assumption coming from a small concentration of vacancies. And of course, I could define delta HF for a single vacancy or for a mole of vacancies. So, that possibility I have. So, let me calculate what is the equilibrium concentration of vacancies. So, delta G is delta H minus T delta S, and in this case I am talking about delta S being delta S configuration. So, in the chapter on thermodynamics, we had seen that there could be many contributions to the microstates, even corresponding to a single macro state, and in this case I am considering a macro state of a certain energy, and the microstates could come from electronic, vibrational, rotational or configurational, and ignoring that the other contributions to the entropy, and I am purely considering the configurational term, which is the dominant term. So, the delta G for putting n vacancies is n delta HF minus T delta S configurational. Now, to find the minimum for the system, that is what is my equilibrium concentration of vacancies, I differentiate this function dou delta G by dou n is delta HF minus n dou delta HF by dou n, and this is what I said, since I do not consider dependence of delta HF with respect to n, that means I assume that my energy enthalpy to put the first vacancy is same as the 100th vacancy, this term goes to 0 and becomes minus T delta S configuration delta n. Dou delta S configuration delta n is k ln n minus n by n, and this is coming from our Boltzmann equation S equal to k ln omega, and for minimization I dou delta G n by dou n equal to 0, which gives me delta HF by KT is equal to ln n minus n by n, and assuming that n by n, that means n by n is exponential, minus delta HF by KT. In other words, n by n is an exponential function of delta HF. Now this delta HF is of course the energy for formation of vacancy, or in other words a barrier for the formation of vacancy, and KT is my sort of the measure of the thermal energy of the system at a temperature T. So, and this is coming of course assuming that n by n is, that means n is much smaller than n, that means the concentration of vacancies is much smaller than the number of available lattice sites. So, n by n I can calculate making this assumption. Now that means if I increase my temperature, so this is my reciprocal and this is a negative, so they cancel each other. Cancel means that their effects cancel with respect to the concentration of vacancies. I heat my system, increase the temperature, then concentration of vacancies would increase exponentially. This is something which I need to note. So we will see, we will try to see what kind of numbers are involved here in terms of this n by n in the next slide, but we note here that this is an exponential function and temperature is contributing exponentially to the formation of vacancies, and you can see that obviously these are thermal vacancies, that is why they are called thermal vacancies. Now if I am talking about not a delta HF is defined with respect to a single vacancy, then I use K in K, and if I am talking about a delta HF for the formation of a mole of vacancies, then I use R at different temperatures. I am not changing the temperature here, I am keeping the temperature constant, but what I do, I start with 0 vacancies and slowly start introducing vacancies in the crystal. That means I am starting with 0 here, and then there will be a 1 vacancy, 2 vacancy, so forth. I increase the number of vacancies here. Initially, because of the entropic stabilization of the system, that means the system is becoming configurationally rich, and my energy of the system, the Gibbs free energy, would reduce along this curve. But after a certain number concentration of vacancies, it costs me too much energy or too much enthalpy to put vacancies in the system, and therefore actually it will lead to an increase in the Gibbs free energy of the system. So this is now my equilibrium concentration of vacancies. That means at any temperature there is an equilibrium concentration of vacancies. If there are lower number of vacancies present, then I can accommodate more vacancies and lower the energy of the system. If there are more vacancies present than the equilibrium concentration, then the system is not in thermodynamic equilibrium, and given an opportunity, suppose you anneal a crystal, copper crystal which has more vacancies. Suppose I took a copper crystal to high temperature and I increase the concentration of vacancies, and there you can see a table here. For instance, at 500 degrees Celsius, if my concentration of vacancy is 10 power minus 10, that is n by n, and if I go to 2000, it goes to about 1 in 1000. Now suppose I quench from here and I retain, for instance, about 10 power minus 5 concentration of vacancies at 500 degrees Celsius, then it is more than the equilibrium concentration. But suppose I keep it at this temperature for a long time, then slowly the vacancies would anneal out. That means it will leave the crystal and atoms would come back into the original lattice positions, and thus the energy of the system would go back to its global minima, which is now the equilibrium, which would correspond to an equilibrium concentration of vacancies. So let me take a typical example of what kind of concentrations we are talking about. Suppose I am talking about FCC metals, and we already had seen the cost. I am having enthalpy cost of putting vacancies in this material, and they are pretty large. It is about less than between 1.74 and about 1.1 electron volt per vacancy. Of course, you can also talk in terms of kilojoule per mole, which in terms for nickel terms would be about 168 kilojoule per mole of vacancies. Then this number for about these FCC metals is about 10 power minus 4 at the melting point. That means now even at the melting point, the fraction of sites which are vacant is still pretty small. It is 1 in about 10,000. So it is not a very large fraction, but nevertheless not a negligible fraction. So this accommodation of vacancies in a crystal actually leads to a very important effect, that suppose I am talking about heating a metal, then we know that the metal would expand. Now the metal would expand because of two reasons. One reason is of course the fact that the atoms are going to vibrate around their equilibrium lattice spacings, and when they are vibrating, you would notice that if you talk about the force displacement curve, the mean position or the energy displacement curve between atoms, the lowest energy position correspond to the equilibrium lattice spacing. When heating it, this energy displacement curve is asymmetric with respect to the minimum, and actually the mean position shifts to larger lattice parameters, and therefore, when you heat a metal, purely because of the vibration of the atoms around the lattice position, the metal would expand. So, this is something which we all know why a metal expands, but there is a more subtle and entropic reason why a metal would expand, which is what we have just now seen, that as we heat a metal, more and more vacancies are being accommodated into the material. How are these vacancies accommodated? The vacancies are accommodated because now, let me enlarge this crystal a little bit and draw a few more atoms. So, as I am heating this crystal, the equilibrium concentration of vacancies has to increase. That means more and more atoms would go and sit on the surface. So, this will become a vacancy and this will go sit on the surface, which will now correspond to a lattice position. So, at even higher temperature, there will be more vacancies which will go on this, more atoms which will go and sit on the surface, and therefore, I will have vacancy here. Of course, I am just drawing because I have a finite diagram here, I am drawing next to each other, but in a larger picture these vacancies would be far away, and there could be one more vacancy, for instance, which is created somewhere here, and this, for instance, could come and sit here. So, even this crude schematic, you can see that as I am heating the crystal and as vacancy concentration is increasing, the crystal is increasing in volume. So, suppose this happened in all 3 dimensions, then I would find that my crystal will become larger with heating. Though this is, as you can see, it is a 1 in a 10,000 effect, and with respect to, for instance, normal thermal expansion also, it has a very small fractional contribution, it also remains 1 in 10,000 or that order. It still nevertheless, purely because of entropy, the system is now expanding. So, there are 2 reasons why a metal expands when you heat it. One reason is because of the normal thermal vibration, the second reason being stabilization of vacancies as you heat the metal. So, the material is going to expand as you heat it, and this reason is a very subtle and very interesting reason, that more vacancies are being accommodated and the material expands because of that. There are also theories which talk about melting, wherein you discuss melting in terms of a critical concentration of vacancies, though we do not consider that here, but we need to note that vacancies play a very important role in many other properties like diffusion or, as in this case, thermal expansion. Now, of course, we should not always conclude that entropically a material would always expand because of heating. A contra-intuitive and a contradictory example would be the case of rubber. For instance, you take a rubber band, and let me draw the experiment. I take a simple rubber band and hang a small weight in. So, now this is my stretched rubber band. There is a small weight here. Now, suppose I heat this system, then actually you will observe, to our surprise, that the material contracts. So, this is my rubber band, and the sort of a crude explanation I will give here, and which is again related to entropy, is the fact that suppose I have a stretched state of rubber, I can approximate it to sort of all the polymeric chains being extended, and the extreme example would be a straight extended example. When I heat the system, as you know that based on the conformations of the carbon-carbon bond, actually this can actually take a coiled configuration. In the coiled configuration, you can see that actually there are many permutations to this configuration possible. In other words, it becomes configurationally rich, because for instance, suppose I want to accommodate this curve could be here or it could be here, but any one of these configurations could lead to a shortening of the length. So, if I have a starting configuration like this and I heat the material, then the material becomes entropically rich because of the many configurational possibilities or multiplicity of states which is provided by these coiled molecules, and because the molecules coil up at higher temperature, the rubber band contracts. So, it is possible that a material not only expands because of entropic reasons, but also contracts because of entropic reason, as in the case of rubber. So, we need to note that entropy, even though being a subtle phenomena, can actually lead to very interesting results with regard to even physical properties like thermal expansion or thermal contraction, as in the case of rubber. So, as you can notice, this force which is contracting the rubber is actually a very subtle kind of force. This is not arising from the typical kind of forces like either gravity or electrochemical forces which we normally consider in a material. This is coming from the configuration of the entire system. So, this we can write as an entropic force. This is not the force of the normal kind. So, this is an entropic force. So, which is very different in origin compared to the normal forces you deal with, as I said, gravity or electromagnetic forces or even a weak or a strong force. So, let me summarize the calculation so far, which is something very important, that in spite of the fact that it actually costs me energy to put vacancies in a crystal, and this energy or enthalpy increase is coming from broken bonds, the fact that Gibbs free energy can actually be reduced by accommodating vacancies implies that I can actually have a increase in vacancy concentration, and that means at any temperature you could have a equilibrium concentration of vacancies, and therefore at any temperature you would actually prefer vacancies when you are above 0 Kelvin. And as we know, 0 Kelvin is unattainable. In other words, at any positive Kelvin you will always have a certain concentration of vacancies in a material, and therefore you can call vacancies as equilibrium thermodynamic defects. This is of course true that every defect can lead to an configurational richness in a material, and therefore there will be an entropic contribution by accommodating the defect, but we will see, as perhaps in the case of dislocations, that actually dislocations cannot be stabilized thermodynamically, or a dislocation cannot be a thermodynamic defect in a material, and this is because the temperature at which a dislocation would actually be stabilized in a material would be higher than the melting point of any available material. So, dislocations cannot be equilibrium thermodynamic defects.